It's not bad, but yeah, I've found out you.
Now I do.
That's exciting. Are there, yeah, it's energy.
Okay, I'm gonna leave now.
Energy space as in companies and energy.
We're all set.
So I'll be joining at
Just start talking.
here.
Good, I guess.
So, like,
Oh, you can hear me.
Stuff like that.
Can we see the chat?
That's really cool.
Yeah, we're good, we're not, we just,
Okay,
An interesting place to be. Yeah, oh, yeah, yeah.
all right. Well, I'm gonna, I guess, start the presentation since we've got some people online. So I'm Christy Green. I'm a research engineer at the Western Cooling Efficiency Center at UC Davis, across the street. And I'm gonna be presenting on an analysis we did of GHG emissions in variable refrigerant flow systems in office buildings. And the importance of this is a lot of times when you think about decarbonization, you might look at just the on-site emissions or on-site energy use associated with installing a particular technology. But in this case, we're going to look at the emissions all the way from the production of either energy or natural gas up to the point of end use. And we're doing that with the VRF system. We're going to compare it to a baseline packaged rooftop unit with B&B boxes that's usually used in commercial building space conditioning. So to do this, we used Energy Plus models, and our model was a PNNL medium office prototype building. So PNNL has a lot of different prototype building models for commercial buildings and residential buildings. We use the medium office one. It has 3 floors with a total floor area of around 5,000 square meters or 54,000 square feet. And it uses X-rays in the 2019 version. It's got 5 zones on each floor. So there's a 4 zone and 5 perimeter zones. And that's just a picture of what it looks like. So a lot of you might be wondering, what are VRF systems? So not many people outside of HVAC are probably familiar or think about this ever in your life. But they are heat pumps outside. So we've got one external heat pump outside the building that's supplying terminal units in each conditioned space or zone of the building by a refrigerant line. The refrigerant goes directly to that terminal unit instead of a bunch of air flowing to terminal units in each of those zones. So it's usually more efficient than a rooftop unit. It has more modularity or compactness. So in especially like historic buildings where you might have low roof space, you can't really get large ducts in there. Having just a refrigerant line might be beneficial. You do still need some ductwork for your outdoor air supply, but less than what you typically need. And you also have a heat recovery option where you can remove heat from spaces that are being cooled and transfer that heat to spaces that are requiring heating. That's another efficiency opportunity. The VRF and DOAS system that we modeled is an in-real measure that they developed in 2023. It's based on cold climate heat pump technology that can operate down to -22 degrees Fahrenheit or -30 feet. And yeah.
I think people cannot see the whole slides, I saw chat problem, they only see the
Oh.
top left part.
Hey, you guys. I need help. They can only see they can't see the slides.
I think it's zoomed in, from the
Zoomed in.
chat icons I saw.
So are they just seeing like?
Yeah, it's zoomed in,
It's zoomed in. Let's take a look.
and we can only see the top left.
Oh,
Oh, well, let's take a look. Let's see what's going on. The top left. Well, we're joining, I apologize for the technical difficulties. We're joining right now. And we're gonna take a look and see what is happening. So let me go ahead and, I'm gonna just escape this real quick. Here we go.
It's not even showing that Zoom is. I think the Zoom crashed, which would happened to me earlier this week.
What about now? Any changes?
No, I can see your mouse. I can see the slides changing, but
Let me restart.
I can only see the first 2 bullet points.
Oh, interesting. Okay, very interesting. I'm gonna close this. I'm gonna stop the share. So guys, hang on. I'm just gonna stop the share here real quick. Okay. Can you see us? Just us, the camera?
Yep.
Okay. All right, thank you. I just need to see what's going on. Okay, we're gonna unplug. I'm just gonna reset everything. Okay,
So Christy, when we
I
cut-
apologize, Christy, for this.
When we cut the recording, we'll just cut this part out.
Yeah.
And so then maybe just say like,
Good.
okay, so we're back, we got it figured out. So. Okay.
I'll be clear.
Let's see.
Yeah,
I'm
exactly.
confident.
I got a call her, but yeah.
What about now?
Perfect.
Yeah, she likes to fight.
Yes.
Okay.
That, wait, actually,
Yeah, that's it.
it's still, we could see more of it, but it's still cut off. Like, for example, on the first bullet point,
Mhm.
where it ends in zone, it only shows like the E's cut off. So I'm not seeing like the bottom right corner. Oh, maybe other folks able to see
Yeah,
all
can
of
other
it.
folks see it? Cause it could be, okay,
Yeah,
so if you,
everyone
so
else.
then.
Oh,
what's
okay.
going on is It's something on your end then,
Okay,
it looks great, okay. All right, well, I wish I could help you.
Thank
on
you.
your end. I would just say disconnect, reconnect, see if that works out for you.
All right.
Sorry about that.
That's okay.
Good thing we were close.
Jumping back in, we're going to edit this and probably cut out everything that just happened, so if you're listening now, I'm just gonna jump back into where we left off with cold climate heat pumps. So they operate down to -22 degrees Fahrenheit or -30 degrees Celsius. They are equipped with the dedicated outdoor air system, so that's supplying all that outdoor air, and that DOAS system has both heating and cooling. Some of the past DOAS models for Energy Plus only did cooling. This does both. The heating is supplied with the electric resistant elements, and there is mention in the report of potentially switching that out for heat pumps later on, which would make the system more efficient. It also has energy recovery ventilator or heat recovery ventilator, depending on the climate. If it's humid, it will be nice, so energy recovery. If it's dry, heat recovery. And our baseline system is just a typical conventional rooftop unit with VAV terminal units. So we've got an RTU associated with each floor of the building, and the supply air, in this case, is just modulated by those VAV boxes. They have dampers that control airflow. And we had several different reheat strategies that we modeled. So we started out with just electric resistive reheat. It turns out that's a pretty significant component of the energy consumption in these systems. So we also decided to try a hydronic heating loop, and we modeled 3 different boiler efficiencies on that loop. In the literature, it looks like while you might have a really efficient boiler, if you've got a lot of bypass happening in the reheat, you might see as low as 50% average efficiency on your boiler. Okay, so now, we went backwards. Okay, there we go. That's taking care of like the energy piece of the modeling, and now we have to translate that into emissions. So the first step we took was with the electricity emissions. We used the Cambium long-range marginal emissions rate to calculate the associated CO2 emissions for electricity used on the site. On the left side, we've got United States mean long-range marginal emissions rates for a 24-hour period across several months. You might not be able to see the numbers because they're kind of far away, but just know that the middle is lower emissions. So that's typically like when you would have more solar energy being produced, and then overnight you've got higher efficiency. So we took those hourly values and applied them to the hourly energy values that we got out of Energy Plus. And that's how we got our electricity emissions data. There are several different scenarios you can use in Cambium. We use just the mid-case scenario. So there's some that assume you've got low renewable energy costs, some that assume you've got low natural gas costs. You've kind of got like 2 extremes of the spectrum, but they're all anticipating different policy or market changes and how that would impact electricity generation. So mid-case for us. And this shows over a 15-year period how that looks, beginning in 3 different years. So 2025, 2030, and 2035. And across the 6 regions that we're gonna look at. So it reduces over time, and then it also varies by region. In addition to the electricity portion of the emissions, we also looked at natural gas emissions associated with the on-site combustion. Anyway, with on-site combustion, with production of natural gas, and also behind the meter leakage of natural gas. And then we also looked at refrigerant leakage, which turned out to be pretty significant in this analysis. For our refrigerant leakage, we assume that the VRF system has about twice the amount of refrigerant charge as the typical air conditioning system. We've got a lot of refrigerant lines, so a lot more refrigerant charge. In the literature, there are a lot of different leakage rates reported in our paper, which hopefully you'll be able to access in a few next months. We did a sensitivity analysis, but here you're just going to see results for 10% leakage rate for VRF and 4% for all the other systems, so the DOAS air conditioning and the rooftop air conditioning. Prior to 2027, we're using R410A, so with the AIM Act 2020, after 2027, low GWP refrigerants required, so we're switching to R32 in our modeling after that. And so we took all that emissions data, refrigerant leakage, electricity data, and we applied it to 96 different cities in the US. So each of these cities was selected to represent a climate zone within a state, within a region, and then the population associated with that location was used to weight the energy result modeled in that location. And then we present those for regions and the whole US. And just to give you an idea of like how the US percentages break down, it's kind of weighted more heavily toward Northeast and Midwest, just because we've got a lot of population centers there, New York, Chicago, so on. So keep that in mind as we look at the results. And here are our results. So notably, the cooling, which is this blue bar, is pretty much the same between the two systems. So any advantages with the VRF efficiency kind of got balanced out by the DOAS. The efficiency is a more or less equate to the RTU system. But we get a lot more savings with our natural gas system. Number one, because the VRF is more efficient. Number two, because associated emissions with electricity are typically a lot less than that with the natural gas. However, really need to look at refrigerant too. So refrigerant is in the yellow bar at the top. And you can see for 2026, we're using R410A, VRF, and DOAS is not really advantageous compared to any of these on an emissions basis because of all the refrigerant leakage. Once you switch to R32, you have some benefit, but there's opportunity for improvement there if we can reduce that leakage rate. And these are our results for each of the regions. So if you look at Midwest and Northeast, after the transition to R32, you've got some emissions advantage in those climates because they're more heating dominant. Other places, especially like the Pacific, where electricity rates are lower emissions, and also we don't have a lot of demand for cooling, for heating, we have more demand for cooling. We don't have quite the same savings, so not as advantageous in those climates. So in conclusion, our low GWP refrigerant like R32 is essential for VRF systems if those are going to be a success. Particularly in colder climates, or places in colder climates is a good application. And we can address the leakage in these systems, that could help a lot. One pathway is with air to water systems where you have a water loop, a hydronic loop going into the building instead of refrigerant that could potentially lead to less emissions. Questions?
You mentioned refrigerant leakage is an assumption you kind of looked at. What about envelope integrity and insulation values? Does that, if that changes for a particular building, does that change the outcome for that different?
So on a total amount it would, but if we were thinking comparing the two systems, you're looking at the relative impact of the systems themselves. So we held those values, constant between them, but they are regionally dependent. So the create typical DOE prototype kind of selected the building construction for that region. But yeah, it's a relative basis.
Right, I guess if there's I recognize this could be on a relative basis and you can choose one exemplar for a particular region. But if you had a range within that, you could potentially treat a building, right, to make it, to improve the insulation value and improve this leak, reduce the leakage within the building of outdoor, indoor air. Does that,
In a prior version of this type of analysis, we
Okay.
looked at like what happens if you change the envelope.
Yeah.
And what we found was that the total emissions go down, but generally speaking, the sort of the emissions associated with the HVAC system, when you're comparing type 1 versus type 2, everything sort of just scales.
it scales.
Yeah.
And
Okay.
so we didn't do that here, but we did it in a previous, in a previous, in a commercial building, it could matter a little more because as you make the envelope better and better and better, you reduce the amount of heating that the building uses and you create more cooling needs, right? Because you have all your, in commercial buildings, you have all these internal loads, and so if we seal the envelope and insulate it really well, then now the heat gets trapped, and so now we need less heating and more cooling. So in that circumstance, you would potentially,
They change a little bit,
yeah, you could
It's a
shift
load
things there, and
change.
then so then that would make the BRF look worse.
Or better in climates that are Southern California or.
Well, no, but the VRF has the VRF makes the biggest emissions impact in places that are heating dominated, so when buildings need the most heating. So it'll look worse in poorly insulated buildings, and as you insulate. But the envelope you used was what year construction?
2019.
So fairly recent, so I mean, they're not really gonna be like better buildings per se, so if anything, if you used older buildings, that might look big. VRF look better.
Right, I'm just thinking
Is
that
my
might be the reality, right? The reality is these are worse, typically buildings are worse than at least code, right?
I would, kind of expect it to just scale, so you're gonna have the same impact for both systems, but it would be interesting, it's another thing you could look at. Any other questions? Can they hear whenever you guys are talking? Like, do I
Yeah,
have
the
to pass this
microphones are
around?
dropped.
Yeah, but it may be a good idea to repeat the question.
So, are there any other questions?
Can you go back to the conclusions?
Sure.
I also just want to point out how we simulated a 10% annual leak rate on refrigerant and VRF systems. Nobody knows this number. This number is not, like, the annual rate of leakage in a VRF system is basically not known. And Daikin, I know you have a relation to Daikin, right? Daikin claims they have some actual data of tracking, like, they've actually been collecting data on a number of VRF systems with some of their service contractors, and they actually have like something that they claim can be used to calculate leak rates, and they're claiming it's like 2%.
Yeah, there have been some
But
discussions about that.
yeah, but I've asked them, could we, I suggested to them that they make all that data available to us and we like write a paper with it. If they like their data, but we review everything. So I don't know, I haven't heard back, but I think it'd be interesting.
And in the paper, we've got like 2 to 18% refrigerant leakage on the VRF, and then is it 2 to 8, I think, on the typical air conditioning system. So the DOAS and the RTU. So we did like a sensitivity analysis, different pairings of that, how it looked for emissions, but
And it's crucial.
It's 10
I mean,
before.
your results complete. No, I don't want to put words in your mouth. I'll make it a question. Do your results change significantly with that assumption of leakage rates?
Yes. Especially if you get all the way down to 2, it changes the answers, it changes,
Yeah.
yes.
it's significant, so.
So that's something to be really careful about presenting, saying that the results are completely predicated on that,
Right.
on that assumption, something that you aren't measuring.
Yes, so we, like I said, those values we took from the ASHRAE standard
Yeah.
assumptions for those, so
Which
that
is
was the one
what,
we-
3% or something?
it was 10% for VRF and
Oh.
4% for the RTA
Right.
unit. So we used those just because it was like a accepted value. But then we explored those ranges to also present that in the paper to discuss how that could vary. But there's such a wide range of potential leakage rates in VRF, and so much of it is dependent on the installer and, you know, how well they did that job, that's kind of difficult to predict. So we would like to do more work on looking at VRF systems and seeing what the actual leakage rates in the field would be like. So if anybody out there is interested.
We have submitted this to energy policy, and I do worry about what Daikin might think of it. But I try to be very, very careful about the issue of rates and how little is known there.
Let's talk about that afterwards.
Yep. Sounds good.
Any other questions? We can switch.
Thanks, Christy.
Yours is on here now?
Yeah,
Okay, so I think you just this and to the presentation.
Theresa, did you talk to Mark about this in the last week or two?
Why do you ask?
What?
Why do you ask?
Because we were in New York. They discussed it.
They were here and I talked a couple weeks ago and I talked to them too, to Daikin directly. But then I sent a bunch of follow-up that I didn't hear.
If the red light's on, it's recording.
Think everything's good?
good afternoon, everyone. I am Ovais. I'm a PhD student. I work with Kelly Kissock, and recently we've been working more and more in demand response and load flexibility world. Previously, when I was doing my master's here, we worked on industrial heat pump integration and overall thermal energy efficiency in industries. But our new project, which looks like it's going to kick off very soon with the CEC, is evaluating load flexibility in cold storage facilities and how can we design or operate a cold storage facility so we can maximize that load flexibility potential and even go beyond that, just load flexibility, and try to reduce their overall KW load during all times. Well, that's some motivation here. So this is, I think everyone here has seen some version of this, but this is a KISO load and net load chart from May 1st, I think, of this month. And if you look at that 4 to 9 or maybe 5 to 9 period, they have a 3-hour average ramp up of around 22,000 megawatts. And this is all non-solar or maybe non-renewable as well. And this has to come online within 3 hours. So this puts a lot of stress on the grid and on the supply infrastructure, on the generation infrastructure. You need to have these assets available and ready to go during all times. And then also you have to keep your spinning reserves throughout the day, so that is also a source of inefficiency on your grid when you don't need them during most of the daytime. So this solar or the duck curve has created some challenges for the grid operation on a day-to-day basis. And if we go beyond just California, this is ERCOT, and the values on the left suggest that they have around 3 times as much load as KISO has. This is a comparative day on May 2nd. And even here, if you look at that again, after 6 p.m. when the solar is going down, they're ramping up their natural gas and they're ramping up their coal. So it's not only happening in California, it's going beyond our borders now. And as more and more solar gets installed throughout the country, throughout the world, this problem is only getting worse with each jurisdiction. And so this problem is happening every day, but the overall peak demand as it has been conventionally seen is also a problem throughout the load year. So there are maybe 100 hours or 50 hours of the year where you need that peak load demand. So you need to have those peaking plants available for those 50 to 100 years. And what that results in is that this is an August 2024 day, which was the record day in terms of power draw in ERCOT region. And the result here was that ERCOT was only left with 130 megawatts of reserve capacity when they reached their peak around 6 or 7 p.m. And their prices, the real-time prices, hit their price cap around $5,000 per megawatt. So you're not only trying to avoid the within the day difference between on-peak and off-peak, you're also trying to reduce these peak 50 hours, peak 100 hours of the year, so that you can avoid these types of scenarios where you have prices going through the roof, $5,000 per megawatt hour, and you're left with a very small reserve capacity, and that if you stretch that out, that might result in a blackout, or that might result in much worse than just this price spikes. So in response to this, the CEC has, or the state of California has a load shift target set in 2030, which is to reach about 7,000 megawatts of load shift capacity. And this load shift capacity is targeted at that peak 100 hours of the year. So they want to reduce that peak 100 hours by 7,000 megawatts. They already have capacity of around 3,000 to 3,500 megawatts currently, and the additional capacity that they're exploring with multiple different ventures is to have an additional 3,500 to 4,000 megawatts of load shift. And they came out with a residential load shift proposal sometime back. They came out with the industrial, agriculture, and water load shift proposal just recently. And all of those are targeted to achieve this 7,000 megawatt load. So coming on to why we decided to work in the cold storage arena or with the cold storage domain. Cold storage can be thought of as a large thermal battery, which you can charge during your off-peak periods. So maybe during early hours of the night, or during when a lot of solar is available, you can pre-cool your facility, or you can cool it down beyond that lower set point that you have. And then when you reach that on-peak period, you can set your set point such that the facility can coast, and you're not drawing power during those on-peak periods. So the inherent capability to act as a thermal battery, you use the cold storage facility as a good opportunity or as a good option to reach to explore demand response and load flexibility. So in a cold storage facility, the majority of the demand is in the refrigeration unit or refrigeration equipment. So 90% of all the electricity gets used in the refrigeration plant. And if you break down that refrigeration end use, most of that is in the refrigeration compressors, which are actually doing the cooling. And then the next biggest thing is your evaporator fans, which are cooling the facility. So if you want to explore load flexibility and in cold storage facilities, our biggest target or our biggest avenue or opportunity is within the cooling system itself. There are some other opportunities with forklift charging stations and timing defrost, or exploring more efficient ways of underfloor heating, but by far the biggest opportunity is within the cooling system itself. And the cooling largely depends on the outside temperature. So this is just total kW of the facility. This includes everything. And on the x-axis, I have the wet bulb temperature outside. And it looks like it's maybe a quadratic relationship between those two. So when the temperature goes up, the facility electricity draw goes up. And if you're a mechanical engineer, I think I see an airfall design here as well. So if you look at the load profile of some of these facilities, this is an actual facility in California. I think this one is in Sacramento. we used a k-means a k-means clustering algorithm to see which loads within the year were matching with some others. We see some seasonal matchup. So on the top left over there, it starts with 1st January 2023, and on the bottom left, it ends at December 31st, 2023. So this is 365 days of load profile data for a facility, and then we've clustered the matching data shapes into clusters. And if we start looking at these different clusters, let's take a look at the yellow one first. It is maybe during the summertime, July, maybe some August as well. Early in the morning, during the day, their facility is around 500 kW. But when they start production, when the outdoor temperature starts heating up, their load starts getting higher and higher. And if you look at that 4 to 9 period, it looks like that's the time when their peak load is also happening. So this is how typical refrigeration facilities are operating in California. And what we want to do with some of these is what's shown here. So we want to have the facility operate as consistently as possible during those off-peak periods. And during those on-peak periods, so maybe here 4 to 9, this is 4 to 9. I know this is a little difficult to read, but wherever the load is going, this is 4 o'clock, this is 8 o'clock, so this is 9 p.m. in all of the different clusters. So you want the facility to be as low as possible during the 4 to 9 period. But the second thing that we also want is not to spike that demand during off-peak periods as well. And this is also an actual facility. This is a real load profile. So this is someone who's doing this in California, shutting down their cooling system during 4 to 9, and also not taking their load up during those off-peak periods. And if we add solar to the mix, so that facility that I was showing also has solar on site, and during maybe around 4 to 5 o'clock, their load starts going negative as well. So this is 0. So at 4 p.m., 5 p.m., they're not only just zeroing out their grid draw, they're also supplying electricity to the grid. So this is our target, and some easy ways to achieve this is just by intelligently operating your facility, knowing what your envelope has, if you can let those temperatures drift during that period, and also just scheduling your production, what comes in, what goes out, at what time. So a simple thing that this facility did was just operate and just bring in or send all of the loads out before 4 p.m. So these are the number of shipments coming through the door or going out. It'd be either way, and it looks like they're done with all of their work before 3 p.m. So their facility they can close the doors on the facility and let it cool down, because most of the load in these facilities are just infiltration loads from the door opening and closing, and also the product coming. So if you have no product coming in and the doors are shut, then you can reduce a lot of that cooling demand. So earlier we explored why load flexibility and load shift is important on a grid scale, but we also need to explore why it is beneficial for the facilities to do, because the value proposition for them would be if they can reduce their demand charges, or if they can reduce their energy charges by doing this load shift, and also maintain their product quality. So here I'm showing just one rate schedule from San Diego Gas and Electric. PG&E and SCE have very similar rate schedules, and the on-peak and off-peak energy charges are about 80% different. So if you're using a kilowatt in on-peak hours, that's costing you 80% more just in terms of energy charges. And there's also an added demand charge on the on-peak hours. So if your overall monthly demand lies in those on-peak periods between 4 to 9 sometime, you might be paying around $75 a kW. So the monthly max, you have to pay that whenever it occurs. But on top of that monthly max, you're also paying your summer or winter on-peak. And if you can reduce this on-peak demand charge, you can reduce $45 a kW. So for example, if you're reducing 100 kW from that on-peak period, you're reducing around $4,500 from your monthly bill each month. So this is the proposition for the facility. And then we looked at around 15 or 16 different cold storage facilities in California in all PG&E, SDG&E, and SCE regions. And we just evaluated what energy savings we might come up with by shifting 100 kW out of that on-peak period and into that off-peak periods that's occurring before or after the on-peak period. So this is not even optimizing their operation. This is just looking at what happens if we just shift out 100 kW. And 100 kW for most of these facilities is like 10 or 20% of their load. Most of these facilities lie around maybe 500 kW of sustained load or around 1000 kW of sustained load. And again, one more caveat here is that we didn't even look at optimizing the demand charts as well. So if we move out the 100 kW and it's pushing up their demand, we didn't even we didn't consider that as well. So if the demand charges go up, they go up. We just did 100 kW load shift and looked at what the savings could be like. So we found out that the savings number, we do end up saving in all of the facilities in all of these 3 IOU regions. And the average savings were about 8%. And we found that we could save for some of them, maybe about more than 10 to 20, to even close to 20% of in their energy costs are through 1 year. So after we've established that there is the need for demand flexibility, after we established that the cold storage facilities could be a good option for achieving this demand response, and that there's also incentive for the facilities to participate in this, we put our proposal in with the CEC, and our research questions then were, how can we design the cooling system, or how can we operate the cooling system to optimize that demand response potential? So how can we predict the space temperatures and then operate the system in a way that that can maximize that shutdown period? If we can do it for 2 hours, 3 hours, 4 hours, what does that window look like, and how do we calculate and optimize that? And then what operational strategies can we adopt to reduce their overall demand, not just in the on-peak period, but throughout their operation? So if they're operating at a consistent load of 500 kW, what methods can we take to bring that down to 450, maybe 400? And those involve energy efficiency, obviously, and then also how is the system operated? We can do some stagger operations, so not bringing everything online at once. We can start bringing compressors on one by one, coasting for a little bit. All of these strategies can come together to reduce their overall demand. And then obviously we're also looking at how can we maximize that demand response period. And then the last one was how can the cooling strategy be optimized with their production schedule? So if they have strawberries coming in at 60 degrees F and they're planning to have 40 shipments of them the next day, we can plan for that. We can plan ahead, pre-cool the facility so that when the strawberries do come in, they're not spiking that demand because they suddenly need to cool down all of that incoming product. So these are our research questions, and this research is just starting out. So I don't have much results, but I can show you the extent of where we've got so far. So our idea here was to design a data-driven prediction module. So that is how can we use sensor data and facility data to predict space temperatures accurately and predict space temperatures over a forecast horizon. And the inputs to this data-driven module would be your past indoor temperatures, your control parameters such as what evaporators you have on, what level of operation are those evaporators at, and then what is your defrost status, what is your underflow heating status, all of those things. And then uncontrolled parameters, what is the outside temperature, what day of the week it is, what day of the hour it is, what hour of the day and what day of the week it is right now, those kinds of parameters, and using all of them to predict your space temperatures for your control horizon. And then using that prediction to optimize that operation. So if you have your outside temperature, your control parameters, your indoor temperatures, you can start optimizing your operation and seeing how can you operate the facility so those space temperatures stay within your within the bounds of what the product can handle, and maximize or minimize your energy costs or maximize that demand response window. So these types of optimizations you can run once you have that prediction module. And then you can also have external inputs coming into this system. You can have DR signals, demand response signals coming in from the utility, or you can have real-time electricity prices if the facility gets enrolled in a dynamic pricing pilot or it has some day ahead pricings coming in. You can have those types of inputs coming into the optimization to optimize the complete system. And then through the optimization, you can then output control signals to the facility and operate the facility as you want. And then, so our structure that I showed you previously was just designing the system, and then how it operates with the facility through a communication architecture, which is automated demand response ADR. I think Lawrence Berkeley has worked a lot on these standards, and they are on ADR 3.0 currently. So you have a virtual top node, that is the utility sending out a demand response signal. You have a virtual end node, which is at your facility, which reads that signal and then decides what to do with it. And then additionally, what we've built in is that we have wireless sensors at the facility that feeds into our data-driven prediction module. We have data coming in from the refrigeration control system. Everything comes into a central server. We can read off that server. We can push our optimization module and our control strategy to that central server, and then it gets sent to the virtual end node, and then the virtual end node can talk with the refrigeration control system at the facility to control the refrigeration system. And moving on, so our first step was to design what the temperature prediction methodology would be, and it's an ongoing research. The methodologies that we've come across so far is just using maybe linear regression, just starting out with linear regression, so we know which parameters matter, where do we find correlation, which are and all of those things, and then we can go beyond to neural networks. We can design a simple multi-layer perceptron neural network, or something more complicated, such as a long short-term model, which works on time series data, and it learns the behavior. It learns short term, what's happening in the short term and what's happening in the long term, and then predict those space temperatures. Or we can go even beyond to something like the transformers, which are being used for time series prediction. These are just ideas right now that we can explore. We can also use autoregressive models with exogenous input. So these models have been used for time series prediction for a long time, and some new additions would be the neural network autoregressive models, which use neural networks with these time series data and control inputs to predict future outcomes. And we can have other methods in here as well. So temperature prediction is complicated, especially when there are multiple zones within the facility. So this is just one facility that had 24 zones, and this grid is showing which zones are correlated with which other zones here. So the diagonal going from bottom left to top right is the zone's correlation with itself, which would be 1. But you see these large red blocks on the top right. After that, a big large red block in the middle and on the bottom left. This shows that the zones are correlated with each other. Either their temperature goes up and comes down at the same time, or they share a boundary, and then there's some temperature leakage between these zones. So temperature prediction, it has to be designed in a way that it considers these beyond the single zone kind of interactions, and this is the reason why we are thinking that a data-driven prediction module is much more better suited than using something like a physics-based module for these multi-zone large-scale facilities. So our temperature prediction problem is a time series prediction problem as we see it. There, we want to predict temperatures out in the future, some k time steps into the future, and our inputs are space temperatures, current space temperature, and historical space temperatures. Our control inputs and our uncontrolled inputs are for the current period, and some and some look back window. And we're using all of this to predict some space temperatures into the future. How we can extend beyond just using historical data is also to use future controlled and uncontrolled input. So we can have a prediction for outdoor temperature, we can have predictions for what controls you want to do at what time period. And then this problem becomes historical data plus forecasted future inputs to predict those future space temperatures. And again, this is our central module. In between, we would have a separate one for each zone, and then we can predict accurately what space temperature we result with in each zone, and then optimize our operation based on all those predictions. So some of the work that we've done so far is look at the long short prediction module, and this looks at your past time steps, your control inputs, your uncontrolled inputs, and your temperature inputs for past time steps, and tries to predict out into the future what your space temperatures would look like. This is just the architecture of that neural network. And then we try to run this at an actual facility and see what type of results are we getting. There was some, it learned patterns and behaviors, but we're still in the infancy of this research, and so the R squared here was about 88%. So the prediction was getting close to what the actual space temperatures were like. But we also want to explore if this is just using past space temperatures and then just outputting a mean, or is it actually learning behavior in response to those control inputs and uncontrolled inputs. And lastly, using those space temperatures, we want to optimize the cooling power. So the next step would be to have a model for our refrigeration facility. And here we've already experimented with some physics-based models, so having a cooling load and then optimizing what compressors are running, how the evaporators are running, and then what would be the cooling power for the facility. But we've also tried to use a data-driven model here as well. And this is a simple multi-layer perceptron deep learning network that learns how your control inputs, which evaporators are on, how much of the VFT step are they on, and what is the outdoor temperature, all of those inputs, and then calculating what your cooling power would be based on all these inputs using just a data-driven prediction algorithm rather than using a physics-based model. So this is how far we've got right now. We're just starting out and it's a long way to go, but that's all.
So in your training data, what time frame are we looking at? Like how much do you need months? Do you need weeks?
In literature, people have done this with a week's worth of data. So they have an outdoor temperature, they have control parameters for all the indoor zones, and they try to predict what happens when a DR period starts or when the cooling system shuts off. How quickly does that temperature start to drift? And the neural networks learn the behavior very quickly, even with a small amount of data. But maybe for some seasonal variations, it might be better to have maybe a year's worth of data. That would be the best case scenario. But most of the patterns can be learned within maybe a week, 2 weeks, and just modulating your system.
You're thinking of having it like as an online type model that's retraining as that goes through the seasons?
Yeah, this would be, I think the idea right now is that we train this after maybe a month or maybe 2 weeks. So we're not online training all the time, but we have a model that's trained on the most recent data. And we keep updating that model parameters when new data comes in, but we have to decide on what frequency would be best. If we find out that there's no advantage in keeping it learning every week, then we might extend that, or if we see that there are changes that we might need to consider, then that training frequency would be much smaller.
And what are the look back and the prediction, those intervals?
So for this, right now, it's we looked back 16 time steps, and this was 15-minute time steps, so we looked back maybe 4 hours. And then I was trying to predict for the next 2 hours, so 8 time steps ahead. And yeah, this is just me picking numbers, but we can see what works best, right?
And you had like some R squared, but do you have any quantification around, you know, your uncertainty of your model output and how that will affect your demand response? Yeah, it seems like you might not be there, but just
Yeah.
wondering.
Yeah, there is some uncertainty, so if I don't have that chart in here, so if I do a y equals x line, at each temperature, there is a vertical line of output, so the model is predicting maybe an average of what it should be, rather than trying to capture all the variation right now.
Yeah.
So there is a certain uncertainty, but we'll see what parameters we can change or how we can modify, maybe the look back window or the prediction window, and maybe change some hyperparameters in here to improve all of that.
Yeah, but on your grid, is that just like a 2D grid of the floor plan? Is it at a certain heights?
No, this is. I'm not sure if this is how the facility is laid out, but this is all the zones within the facility. So there are 24 zones. But I'm not sure if these are laid out the way that you see it.
Okay.
Oh, just what, you said something about underfloor heating. Why is there underfloor heating in a cold storage facility?
To keep that floor temperature, I think comfortable for people to work on.
Okay,
not
like,
have
and
no
maybe like
on-site.
prevent ice or something?
Yeah, they also get ice and then just condensation on the floor and just water, so avoid those things.
It's so the floor doesn't heave.
Huh?
It's so the floor doesn't heave. Otherwise, the space is too cold. You get frost underneath the concrete and they'll buckle the concrete and then all the racking will fall down.
Wow.
And then finally, just one other question. Early on, you correlated compressor power to outdoor air wet bulb?
Wet bulb, yes.
What, I would think that for rejecting heat outdoors, I would think that would be better correlated with dry bulb temperature.
Possibly.
You might look at that.
So when you're looking at temperature prediction, it will be interesting to ask the question like how much benefit you gain with a better forecast in temperature. Because sometimes, if sometimes you have an uncertain forecast, but it doesn't degrade that much to your system, and sometimes like having a really tight forecast like really improves the system. So maybe that's a question you're not exploring.
Yeah,
How important is to actually predict temperature?
yeah, I think it would be important here because there's food storage and they have a maximum allowable limit of what they would allow that food to reach. And most of these facilities, so the one that we're working with, they have a limit of 0 degrees F. They let the air temperature drift a little beyond that 0 degrees, but the idea here is that the air heats up faster than the product. So the product is never going beyond that 0 degrees. So we would have to have some accuracy around our prediction. So our product is not the product quality is not suffering.
But then in that case, like when you make a bad prediction, you can still adapt on the
Yeah,
spot,
because
right?
this is kind of just doing maybe 15 minutes or 1 hour ahead. If we start drifting, then the model or the prediction can correct itself if it starts reading higher temperatures from the sensors.
On an absolute basis, kind of what's the range of savings? Like you said, 500 kW on average, so it's a 4-hour window a day, $75. Like, I'm calculating what, $6,000 savings over the course of a year? Is that, am I wrong, or is it closer to?
So it would be much higher than that. So this bar chart, this is just showing what happens if you do 100 kW of load shift out.
100 kW.
100 kW from that on peak into that off peak. But what I showed with this facility here was that they are shutting down during that on peak and it is not affecting their off peak operation as well. So actual savings would be much higher. And they're not doing 100 kW, they're doing maybe 500 kW during the summer and yeah, maybe even 800 to 900 kW during the summer. So those were just to give us the idea what happens, what saving potential are there. And then the actual, if we go in and optimize, then we can even do better than what's happening here.
Could you go back to the, your airfoil?
Yep.
I'm sure you've studied this intensively already, but it sort of suggests that maybe there's some other kind of trends going on in here, maybe with respect to time of day or some periods of declining temperature. Well, I guess it comes back to, you see this a large range in power consumption over the same temperature.
Yeah. Yeah.
So is there a dynamic going on there? Or is it on the increase? I don't know how to describe this very well, but have you studied this in more detail?
Yeah, we've looked at, so another big factor is what their production looks like. When is their product coming in and going out? So those are the periods that are, that your cooling demand would go up. And, yeah, I think, and that gets translated into time of day and then day of the week. If they're operating on weekdays and not on weekends, then you would see that difference in the day operation. And then if their product is only coming in from 6 to 3, then you would see a higher cooling load between that 6 to 3 period than the later hours. So there is another big correlation with that productions or their production schedules.
And with respect to thermal mass, is it possible to introduce some thermal mass into the building that can be drawn upon very quickly in a sufficient size to make an impact on these results?
Yep, so when we were talking to the facility manager earlier, they told that if the facility was totally empty, there was only air inside, then they wouldn't be able to shut it down for 4 hours. So having a lot of product in there that has a higher CP and that can sustain its temperature, that is what allows them to shut down. And so increasing that thermal mass does help to kind of drift for longer hours. And people have installed, I think I have seen a couple of companies who do maybe PCM installations. So phase change materials that increases that thermal mass. So that could also be an option to look into. So yeah. Option.
So you went through the chart and you categorize the zones, right? So is there anything that you decided, like, have you taken that decision, okay, this is how, like, the similarity is between, like, did you categorize them? Or is it still like no matter what, so anything just like, then your problem is gonna be very big, right?
Yeah, so right now you can call this as a practice facility for me. We're not working with these people, and I cannot call them up and ask and go and visit and see everything. So this is just some pre-work, but once we start with our project, our facility has 12 zones, so we would go into more detail on how which zones are correlated with which others, and then we can cluster them together and then maybe do some other analysis there as well.
Does campus have any cold storage facility?
I haven't explored, but there might be some.
For post-harvest, kind of.
Just basically a place you might be able to experiment with.
Okay, yeah, I haven't explored that, but that's a good idea.
Yeah, I wonder if somebody in food science technology would know. There's a post-harvest technology research center on campus that might. I'll try to find it. For you. Good job.